So now recording should be going about 20 minutes in. Starting right on time. So, hello, welcome to the stream number 7, working on with my work on the Gunship game engine. Last time we finished up the initial work with resource loading, related parallel resource loading under the new all parallel asynchronous design. Under this design, I can do something like await and do load mesh and load material, and I can specify an arbitrary number of resources to load off of disk, and they would all be loaded in parallel asynchronously. And now once they all load, the calling code resumes and continues doing its work. Now the next challenge to overcome is I've got to actually do something with those loaded resources, and the goal is to be able to take that mesh, apply the material to it, and get the scene rendering. And the very first step of that is being able to interact with the scene graph in some way by building up nodes in the scene graph. And that's where I left off on the last stream. And if you watched the last stream, you saw that for the last 20 minutes or so, I kind of rambled incoherently because I didn't really know what to do to get this the scene graph working. There are a lot of hard to answer questions about how this should be built, and so I spent the last couple of days giving this some thought about how would be the best way to implement a scene graph. I've already gone through this a number of times by myself, but I've never tried to do it in a multi-threaded context, and that introduced a number of additional concerns that makes it even more difficult. So what I'm going to do is I'm going to go over, at least at a high level, what those concerns are, and then I'm going to describe what my proposed short-term solution is going to be, or at least I don't know if it's actually going to be a short-term solution, but my proposed initial solution that I'm going to start with and potentially iterate on will be. So the idea here of what I'm trying to build is a scene graph. The idea that each of the nodes in the graph describes some transformation that can be applied to an object in the world space. We call each of these transform objects, following the pattern of Unity, because that's where my experience is. Each transform describes the position, the rotation, and the scale of an object somewhere in the scene. Transforms can be hooked up to each other in a parent-child relationship. So a transform can have 0 or 1 parents and 0 or more children. When a transform has a child, its transformation is applied relative to that parent. So let's say you've got a parent transform at 0, 10, 0, so up at 10y, and then you've got a child transform whose transform is 10, 0, 0, so over 10 on x. Since the child's transform is plus 10 on x, and the parent's transform is plus 10 on y, the child will ultimately be rendered at 10x, 10y, 0z. So child transforms are applied relative to their parent. Generally, when you are using the scene graph system, say you're looking at one of the nodes in the graph, one of these transforms, you have a way of finding out what the parent of that node is and enumerating the children of that node. Once you can do that, you start running into problems with the way that Rust enforces shared mutability. Rust doesn't like you having multiple mutable handles to the same data in memory. This is not really just a Rust thing. This is something that's unsafe in any language, but Rust enforces it. Rust really takes it seriously and wants to make sure that you're not you don't have shared mutable access to the same memory, because when you do, there are a lot of bugs that can only occur when that happens. And if you cut out shared mutable access, you cut out a whole number of bugs that are normally very annoying to pick out, bugs that are especially difficult in concurrent code, which is exactly what I'm trying to do. So let's take a look at just how that happens. Let's say we've got a function here that takes a transform, and we have a way to access the parent and transform of any given, or the parent and children of any given transform. So transform is a mutable reference to a transform object, but if we can access the parent of a transform, and then we can access the children of a transform, it's trivial to say, like, hey, go to the transform's parent, and then go to the children and find me, and get me a reference to that child. And now alias is a mutable reference to transform. And as far as the Rust compiler knows, the Rust compiler can't tell that these are the same. As far as the Rust compiler knows, these are mutable references to two different transforms. Now in practice, this may or may not be a big deal. Depending on what you're doing, this may or may not cause problems. My goal in writing a game engine in Rust would be to actually take advantage of the safety facilities that Rust provides. You know, if I'm just going to do arbitrary shared mutable state, I may as well be writing this in C or C++, because those languages will make it a lot easier to do that, frankly. But I think the safety facilities that Rust provides are valuable, and that they're going to ultimately make it easier to do game development and easier to write better games. So fighting Rust on its safety facilities is just going to make things difficult for me. And so this is the exact sort of thing that I want to avoid. Whatever the API for transform is, I don't want it to be possible to just trivially violate Rust safety facilities. In fact, anything that does potentially violate safety and can lead to memory issues should be, marked as unsafe. So potentially transform.parent and transform.children should be unsafe functions and should be doing this, which eases my conscience a little bit, but still doesn't solve the problem of, okay, now your primary way of interacting with the scene graph involves unsafe code. And I don't know if I've stated this, but one of my goals in writing a game engine in Rust is that it should be possible to write a game without any unsafe code. Games should not include any unsafe code. Any unsafety that's necessary to make it easy to write games should be encapsulated within the engine and handled in a way that then exposes a completely safe and hopefully completely ergonomic API. So this is effectively a no-go for me. Being able to access the parent and the children is incredibly dangerous, because now you can easily get mutable aliases. We could solve this by removing one of these, like, oh, you can only walk up the tree and get parents, or oh, you can only walk down the tree and get children. It's an option. It poses some more interesting questions about how usable the system is, but that is a way that I could go. I could make it so that we can only get the parent. That is not the only problem, however. There are a number of other, there is another concern, specifically with what other mutations are we making to the scene graph that are potentially going to involve interactions between transform nodes. So let's think about it this way. When you have a transform, transforms can be looked at in both local space, which is relative to the parent, and global space, which is absolute in the entire world. If you are only interested in making transformations in local space, then it's incredibly safe to be able to make those transformations. If you have a reference to a transform, like a ref mute to a transform, or you own the transform, whatever the case may be, it's always going to be safe to mutate that, to transform that transform in local space because it doesn't touch anything else. Applying a local translation and trying to move it in local space or scale it in local space doesn't require that it know anything about its parent. It doesn't require that it know anything about its children. You can just basically write directly to that internal data. Specifically, we've got transform data, position, rotation, scale. All you do is mutate position, rotation, or scale, and it doesn't touch anything else. And assuming that we're obeying Rust safety rules, where there's only going to be one mutable access to a transform data object at any given time, then it's always going to be safe to just, even in parallel, to mutate local position, rotation, and scale, because you're only talking to data. You're only looking at data that has unaliased mutable access, which is great. That's actually something that Rust makes a lot easier for me, because I know Rust is helping me guarantee that invariant is never violated. The problem comes in when you try to make transformations in world space. So, in this little draft version that I put together, we also have position derived, rotation derived, and scale derived. That's because we derive the world space position, rotation, and scale by applying the local position and scale on top of the parent's transformations. And so now if you want to say, I take this transform and move it 5 units over in world space, in order to make that calculation, you have to go to the parent and find out what the parent's coordinates are. And you've got to use that to recalculate position derived. Now, for the most part, that's not going to cause any memory unsafety. In a single-threaded context, I think that would be completely safe to do, because all you're doing is reading from the parent data. So even if there's a mutable reference in this somewhere else, like a live mutable reference to that data, we know as game developers that it's safe to do. It's safe to go find that parent transform data, read its position, and then use it to recalculate the child's position. And so, I could achieve that with some unsafe code. It starts to get hairier in a multi-threaded context, because now you have the specter of data races. Potentially, the parent could be another thread could be writing to that parent's global position, or to its global position, at the same time as the child is trying to go read from that global position, and the child could wind up reading data that's not valid. Classic data race situation, it could just do arbitrary, effectively undefined things. So in order to achieve that, we would need some amount of synchronization. And it becomes a question of how worthwhile is it? How often are we moving things in world space? Because let's say we don't do world space transformations at all. We only allow transforms to be manipulated locally. It removes that entire need. We don't need to make points, quaternions, and vectors be atomic, or we don't need to wrap them in mutexes or read-write locks. And so it avoids a lot of synchronization. All we have to do is locally do our local transformations, and then before we do our rendering, go through the entire graph and recalculate the world positions for anything that's out of date, which you have to do anyway in order to do your rendering, because rendering has to happen in world space. So potentially, while it's maybe annoying, cutting out the need to do world transformations and only doing local transformations on your scene graph is going to make this a lot more thread safe and a lot faster by avoiding the need for synchronization. The last concern that I have been thinking about is the issue of changing parent-child relationships. And this gets into the way that I am choosing to represent the transform data in the background. So, a kind of trivial way to represent the scene graph would be to do something like, have transform be transform and then parent option star transform children Beck transform or something like that. Something like that. Ownership is weird, but let's just ignore the whole ownership issue and just say this. Like, parent has a reference to the transform, children has a reference to the transform. Maybe they're like a box transform or something. And we only ever pass around box transforms. Well, this would make it really easy to, given a transform, you can walk over the entire scene graph. And let's for a second ignore the whole issue I just brought up of mutable aliasing when you're able to access the parent-children transform. Let's say that these aren't publicly accessible. They're private. I can only access them from the engine in unsafe code. So I know that I've made sure that it's not actually doing anything unsafe. So now when it comes time to say, like, oh, I want to take one transform and make it the child of another transform, it's really easy to say, okay, the child transform, make its parent the other one, and then the parent transform, add the child to its list of children, and then we're good to go. And then when it comes time to render, the engine just needs to like secretly ferret away a pointer to the root transform, and it can then walk the entire scene graph in order to do whatever rendering it needs. And same goes for all the other systems that need to access the scene graph, stuff like collision detection and physics and whatever else. The problem with just doing this in the way where, we heap allocate every node in the scene graph and then keep pointers to all the other ones, and then we recreate that. That's kind of effectively what I'm doing, is I'm creating a tree structure with a bunch of heap allocated nodes. And anybody who's got some familiarity with, high performance programming, which is especially prevalent within game development, immediately thinks like, oh, when you're heap allocating a tree structure, you're creating a performance hazard for yourself. Especially when you've got data that is regularly there's going to be a lot of it, and you're going to be looking at all of it, which is effectively what we have to do when we're flattening our scene graph for rendering, when we're iterating over all of it for rendering, or especially for collision detection and physics, which have to be very high performance and have to be accessing this data constantly. Heap allocating it at random is a bad idea. It violates cache locality, which causes a lot of memory performance issues. So the way that we really want to do things is instead of heap allocating each node separately, we want to manage it in a set of rows where if we break this up into a series of rows, we've got, row 0, we've got maybe like 2 root transforms. We've got T0, T1, T2, row 1, then we've got child 0, child 0, child 2, child 2, child 2. So these are children of these ones. A, B, C. And then row 2, we've got child A, child of 0A, child of 0A, then we've got child of 2C, child of 2B. And so the setup is effectively, the scene graph is broken up by depth, where all of the nodes that have no parent are at row 0. All the nodes that, all the children of those initial parents are in row 1. All the children of those are in row 2, and so on. And what this enables is very fast updates of the scene graph. So let's say we touch the local positions of every node in this graph. And so we have to iterate over all of the nodes and recalculate their world positions based on their parents' world positions. What we can do is we can iterate over all of the ones in row 0, and we know that we never have to check their parents because we know they're at the root. Then we can iterate over all of row 1, and we know that the parents are never going to be out of date because we've already finished calculating all the parents' world positions. And then same goes for row 2. We can iterate over all of row 2 because we know the parents' transforms are going to be up to date. So all they need to do is look at the parent, calculate local. And so each of these rows can be processed, all of the elements in the row can be processed in parallel. And then once one row completes, the next row can be processed in parallel. And also importantly, these can all be allocated contiguously. These can all be done in like a vec. See? Actually, more what I want would be use the vec macro to represent this. Doing this means that we have cache locality, we have the ability to do efficient updates, we can process chunks, rows in parallel, we can do really efficient SIMD updates. You use SIMD representations for these data to allow for just crazy fast updates. So even if one of these rows has tens of thousands, hundreds of thousands of transforms, if we're talking about a huge scene with just tons and tons of nodes, we can still do very efficient updates on these. What the problem that this poses is now nodes can move around in memory. So, let's say I've got T0, let's say I've got T1. T0 has children, T2 has children, T1 has no children. Let's say I want to make T1 a child of T0. That means that in memory, T1 physically moves around and has to go to the next row. And so, one, we can't just hand user code a pointer to this data, because we've got to somehow be able to update that pointer. That pointer is going to be invalidated every time parent-child relationship changes. The problem, and then there's not just one pointer to that. So one, we've got to encapsulate the representation of a transform that we give to game code in order to make this safe. But then we also have the problem of, T1 didn't have any children, but T0 did. So let's say we want to make T0 a child of T2. So we move this one to the second row, and this is now a child of T0, child of T2. But now all the ones that were childs of T0 have to get moved down to the next row. But then all the ones that were childs of any of those children have to get moved down to the next row in turn. And so entire sub-hierarchies have to be moved around. Now, this seems crazy inefficient. However, we don't generally anticipate the parent-child relationships changing. We expect that to be a fairly infrequent operation. More often than not, it's, sub-child hierarchies getting created and destroyed, and even that is less frequent than just nodes being moved around. So what we really want to optimize for is the case of we have to iterate over a row and recalculate parent-child transforms, because that's what we're going to be doing most frequently. And so that the system optimizes that case, but it does open up a number of implementation questions. And this whole representation of we have to have all this transform data kept in packed arrays that is managed by the game engine, and then we have to hand off some kind of handle to this data to game code. It informs our implementation, and it also means that we've got to think really carefully about what operations we allow game code to do, or how we allow them to do those operations. Because remember, I was talking about local transforms, always safe to do. Derived transforms require that you need to talk to your parent, which becomes a hazard in a multi-threaded context. And then changing parent-child relationships is potentially moving a bunch of these nodes around in data, which is potentially violating or potentially invalidating a number of pointers to that data. So with all of those concerns in mind, the solution that I have come up with, at least as an initial implementation, an initial way to make that possible, is to limit your interaction with transforms to creating them, destroying them, changing their applying local transformations, so changing local position, rotation, and scale, but you can't read or write global position, rotation, or scale. And you can change parent-child relationships, but you can't query what the parent or child of a node is. This is a highly constrained scene graph API. I don't think I've ever seen one quite this constrained, and I have doubts about how usable it will be. But the important part is it's going to be relatively easy to implement compared to a more useful scene graph, and it's going to minimize the amount of overhead that there is in synchronizing access to the scene graph. So I should get a fairly fast implementation that at least gives me the minimum set of operations that I'm going to need to do. And this will allow me to get through this initial example, this initial experiment onto the next one where I start to do actual more like gameplay stuff, get some interaction with the user. And then once I get to that point, I can see what functionality is regularly needed in implementing gameplay code, and I can see what it's going to take to get that functionality. So this is really this is like a first step that gets me to the point where I'm writing gameplay code, and I can start really deciding what my scene graph API needs to look like and what it's going to take to make it safe to use in a multi-threaded context. Okay, that's all the explanation out of the way. I can finally get back to writing this code. I'm going to pop off for a quick break, get myself some more tea going, and then when I get back, I'm going to start implementing this crazy, ridiculous system. All right. So let's get started on this terrible, terrible scene graph implementation. So if we start designing API first, I want to make it fairly easy to create transform nodes. I want it to be fairly idiomatic Rust, so I'm going to go with transform new. And I want this to return a transform object. The idea is going to be that transform is an owned handle to the actual transform data. Ultimately, the engine is going to be the one that owns the real transform data, like the data that has that contains local position, like local transformations and the cached off derived transformations, as well as the information about parent-child relationships between transform nodes. But in order to have gameplay, this internal representation is incredibly unsafe. So in order to have gameplay code, to allow gameplay code to have safe access to this inner data, we do this owned transform, where transform is a non-clone type. It has drop semantics, and so when you create a new transform, it creates the corresponding transform data in the scene graph, and then you must have mutable access to this this transform object in order to interact with the scene graph in any way. And that's going to allow us to enforce some invariance about the way that the scene graph is accessed, and will ensure that gameplay code can never have any safety violations, even in a multi-threaded context. But we are going to have to think carefully about each of those transformations, each of the changes that you can make to the scene graph, because each of them has implications about what we have to do to enforce safety. So we're going to start with the easiest one, creating a new transform. Relatively straightforward as far as these go. The only one that would be easier is making local transformations. So the things that we start out with is transform, which is going to do a thing. I'm not even going to start with this. We're just going to start off with transform. We know that we need transform data in order to actually contain stuff like position, rotation, scale. Then we need a transform graph. A transform graph is going to be, internally, it's going to hold a list of rows, and each of those rows is going to be a list of these transform datas. Transform data is pretty easy. We have position, rotation, scale, and then we have a cached off derived position, rotation, and scale. And these are just meant to be cached frame to frame. The more troubling part is this one. The part where we have to have a pointer to the parent, and we have to have a pointer back to the transform, which is where things get scary. And the way that I initially implemented this was transform in the original code, the component-based one. And I will occasionally be popping over to this for reference. It will probably look like nonsense to anybody in the audience. Don't worry, it kind of looks like nonsense to me too at this point. That is why I'm re-implementing it. So I need a pointer back to the transform. And the reason for that is the transform needs really a pointer to the pointer data. Star mute, transform data. Transform is going to have a pointer to transform data. But occasionally transform data is going to move. We saw that when you change parent-child relationship, transform data has to physically move around in memory in order to maintain this row-based scene graph structure that I want, that gives us the efficient updates that we want. Which means if transform is given a new parent, or one of its parents somewhere up its parent hierarchy is given a new parent, it's going to be moved to a new row. And when that happens, transform data needs to be updated. Now, if all we were doing was impl transform put function set parent ref mute transform. If all we were doing was this, we wouldn't need transform data to point back to transform, because what we could effectively do is, we could do, pseudocode implementation, let data equal remove from row self.data let self.data equals insert into row parent dot row +1 data. So the idea here being, if a transform is only ever moving itself within the scene graph structure, it's only moving its own data to a new row, it can update its own data pointer after that move happens, no problem, and then data never gets invalidated or is never out of date. However, because there's potentially deep complex hierarchies, let's say you've got one node and its parent's parent is now made the child of some other node. That or the node that we're talking about is now going to be moved to another row, but it doesn't know that. It's some other node further up the hierarchy is the one that got moved. And so now how do we update this transform? This transform's pointer to its transform data is going to be out of date because it was moved to a different row and it doesn't know. So in order to achieve that, we need a pointer back to the transform. And this is where things get a little bit hairy. Transform is not heap allocated. The whole point of transform is we hand it off to the user data. So, transform new should just be returning a transform, not a ref transform, not a box transform, just a transform. Put function new transform. I'm going to slap a sexy unimplemented on that. So we can't just, transform data can't have a pointer to this transform object because we don't know where that lives. We can't, that's going to potentially move around in memory if it gets passed to a different function, if it gets put into an object on the heap, or put into another struct that gets moved around between the heap and the stack, and it gets moved around all the time. We can't take a pointer to this because it doesn't have a defined address in memory. If this were C++ and we had C++'s crazy weird semantics, we could in theory, use the move constructor to get a reference to this every time it moves, but even then that's not safe because you might have move elision or copy elision or something, blah, 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 blah. We don't really want to do that. That's a terrible idea. Trying to take a pointer to something that that moves in memory and you don't control when it moves on memory, it's not just moving around on the heap in a controlled way, it's moving around in the stack in potentially arbitrary ways based on what user code is doing. That's a terrible idea. And Rust is right to not give us any kind of move constructor or any kind of way of knowing when an object moves. You have to control the object and be the one to move it to know that it's moving, which is the safe, sane way of doing things. But that does mean that we need a centralized rendezvous point that never moves in memory, that both the transform handle and the transform data can talk to. Now, in my original implementation, what I actually did was the transform was that safe rendezvous point. And if we find where we did things, the transforms themselves were always boxed. Ooh, geez. Oh boy, that's odd. I don't know if you saw that, but when I tried to highlight something that was folded, it opened up. But it didn't happen just there. I don't know. I don't know, and I don't super care. Wait. Is it happening? Okay, I don't know why that happened. So anyway, transforms were always boxed, so they're always heap allocated, and it was safe to, take a pointer to them, unless, those pointers were invalidated. But the whole point of the system was that it controlled that and made sure that never happened. But then when you wanted to get that transform from user code, you didn't get the own transform, you got a reference to it. So you effectively also got a pointer back into that box. And so that's how I got around that. But my goal now is to make transform actually a handle type. So transform has to be returned by value. I can't return a reference to it. So now we need an intermediate. And that is what transform inner is meant to be. So now we actually have a star mute transform inner. Transform inner is always going to wind up being boxed. And then transform inner has a pointer to transform data. Transform data has a pointer to transform inner. And so whenever we move a transform data around, all we have to do to make sure that the pointer that the transform has stays out of date is we go, transform. We go to, all we have to do is do, if we have data ref mute transform data, then all we have to do is, data dot transform data.transform dot data equals data. And then we have to make sure that we do this every time we move data around in memory, but that ensures that no pointers are violated. This does have the annoying fact of, for every transform that we create, we have to both append this transform data to a vector and then heap allocate a transform inner. We will eventually be able to reduce the cost of creating this transform inner intermediate by block allocating them. Really all these transform inners it's just a pointer. So it's a single word size, which is that's not a ton of memory. It's not a ton of wasted memory per transform data. And eventually what we'll do is, we'll pre-allocate the space for it, and then we'll block allocate each of them. So instead of just allocating it at a random spot in the heap, we'll have a pre-allocated buffer of memory that we know where these transform inners are going to live. And once one bucket is emptied, a new one will just be dropped back in that same bucket. And so it'll keep all of our transform inners contiguous in memory, which helps cache locality. And it keeps us from having to just allocate single pointers on the heap, which is probably, I knocked my makeshift microphone stand. I don't know if that came off super weird on the audio. Probably did. So that's what we're going to do. The one last piece of the puzzle that I have not quite thought about yet is the transform graph. This is the structure that actually owns all of the rows of transform data. Something has to own the transform graph, so we actually have to do impl transform graph. We need pub function new. Oops, my alarm's going off. We got to do pub function new. We got to get ourselves a transform graph. This one's fairly easy though. Transform graph. And then we're going to do rows is going to be a vec with a vec with capacity. And what we want now, this is a fun one. Const row capacity use size equals 1,000. And so here's where things, this is another interesting point. I mean, I don't know how actually interesting it is, but when we add and remove these transform data objects to each row, we don't want it to reallocate the vector. I mean, really, I'm using vec right here, but what I really want is something like a stable vec, which isn't a type that exists, but it's a hypothetical type where it's a vector in the sense that it contiguously allocates chunks of memory, but it never, when it reallocates, when it has to get more space, it doesn't copy the old data. It never moves the data around. I want to be the only one that ever moves this transform data around in memory. So what stable vec is going to have to do, which is something that I'm eventually going to implement, is stable vec is going to have some clever allocation scheme where it does a linked list of buffers is one potential option, where it allocates a buffer of a megabyte of data, and then if we ever overflow that, if one row ever needs more than like a megabyte of transform data, it'll allocate another buffer someplace else and do a linked list between it, so that means that each time when we push a new transform data into that row, it doesn't move any of the other transform data around. And that's just, it avoids one more case where I'd have to go and fix up pointers that have been invalidated. But we don't have stable vec now. We're going to fake it currently with using vecs with pre-allocated capacities. And then when we add a new vec, whenever we add a new row, we'll just make sure we pre-allocate it with row capacity. So we'll make sure each row has enough space for 1,000 transform nodes. And whenever we go to push a new transform on, we're just going to assert that beforehand we're going to assert that the actual number of elements in that row is less than the capacity. Because we know that once we push up to that, once we reach that capacity, the vector is going to try to reallocate, and that's not going to be helpful. Also, I'm going to make it 1024 because I'm a good programmer who uses powers of 2 for everything. So obviously, you're not a real super elite hacksaw if you don't use powers of 2 for every constant. So that I believe is all of the players that we need to be concerned about for now. I think we're going to start with transform graph, because the first thing I need to do is I need to create a transform graph at start off. It's got to be owned by the engine. And then I need some way to get at that transform graph. I mean, that's pretty much already handled because I kind of already have a way to get at the engine, but that is going to be my first challenge. What the heck is this? I don't even know how that file got opened. Is this the right one? This is absolutely not the right one. Async engine. This is the one we want. So, fold 1, pubstruct engine. So right now, engine has a window, it's got a render message channel, we've got a mesh map, and then the next thing we want is a scene graph. Scene graph, transform graph. And to get that to work, we need to import async transform, use async transform graph. I'm going to PQRST, okay. Yes, I do need to go through the entire alphabet in order to figure out what letter comes before another one. So inside Engine Builder, I now have to make sure we get a new scene graph when we create it. Scene graph, transform graph, new. And then the next step is going to be actually getting at the that instance. So let's take a look. Do I have any equivalence yet? I do not. I previously had implemented a way to get at the renderer, but now I need a way to get at that scene graph, because effectively what transform is going to do is transform is going to do let scene graph equal do something to get at it. And then what we're going to have to do is, scene graph dot I'm going to do let inner equals scene graph dot create node. We're going to assume that that adds a new transform data to the first row, and then returns a boxed transform inner that contains that data, or probably not a boxed transform inner, just a pointer to a transform inner. And then we're going to do transform inner. Straightforward enough. And so transform graph function create node refmute self. And so then what we have to do is create. So we have a few steps. First we have to create inner transform. Let mute inner equal box new transform inner data, and we're going to start this out as pointer null mute. Then we're going to do create transform data with pointer to inner. And the next step will be hook up inner pointer to data, inner's pointer to data, and then let's say this last one will be a star const transform inner. I believe I had this set up to be star mute transform inner. This actually wants to be a star const transform inner, because transform inner doesn't, we never want to be, ooh, do we? We do actually want to be occasionally changing the pointer to the transform data. I was thinking we never want to change transform inner, but we do, because occasionally that pointer will be changing. So it's going to be a star mute transform inner. Lots of unsafe code. I feel like half the time I feel like I'm not using Rust right because I'm doing so much unsafe stuff, but on the other hand, that kind of is doing Rust right. Like, you want to take all, like, when you're building something like a game engine, you want to take all your unsafe code, put it in a library where you carefully make sure that things are still safe and you provide a safe API, and then your actual application code is all safe code, and you know your application is robust, and all of your bugs, any like memory safety bugs, seg faults, crashes have to be within the library code, which is a nice piece of knowledge to have when you start doing any debugging. So we create a transform inner. So first thing we have to do is we have to assert self.rows 0 dot lane less than row capacity. Row 0 exceeded row capacity. Oh, and the scene graph is something that I'm definitely going to want to write tests for. However, I don't know if it's going to be worth it to do that just yet, just because I expect the API to be changing so rapidly that writing tests for it is going to turn into something of a nightmare. I believe I will probably be testing it just through usage alone. Also, I forgot about my tea, and now it is a bit cold. Sad, but still a little bit warm. This is a raspberry lemonade tea. It is very tasty. So we're going to do self.rows 0 dot push transform data. I'm going to do a transform data new. Ref mute inner transform data new. Just so, because I mean, I think there's probably only going to be one place where I'm creating a transform data. Yeah, this is honestly I'm going to say there's probably only going to be one place in code where I'm ever creating a transform data. So my general policy is I don't create helper functions. Like, I don't create a function for anything unless it's going to be called from more than one place and it's non-trivial. I don't like having a ton of helper functions for a ton of stuff because it makes code... It makes it harder to follow the logic of your code if you're constantly jumping between functions to see what's happening. And it also makes it easier to... It makes it tempting to call helper functions from the wrong place, like use them inappropriately just because they seem to do roughly what you want to do at any particular piece in code. John Carmack has a fairly well-known article, or at least like transcripts of an email chain where he talks about why this is like why he has gone to follow that principle, and I am inclined to agree with him. I prefer my code to be... I prefer to be able to see in a line everything that my code is doing. So reducing the number of helper functions that are only used in one place makes your code generally a little bit easier to follow. And plus, it doesn't hide the complexity of your code. If I broke all of these down into helper functions, and then I just called 3 functions here, I wouldn't be able to see that there's actually a bunch of really complex stuff going on in here. There's trade-offs and argument, and there's places where it does make more sense to do it, but in this case, I am not going to make a helper function for creating a new transform data object. So we're going to do transform. Oh, this is going to be star mute transform inner. Transform is inner. It's actually going to be a ref mute inner because we have to convert this box into a ref mute, and then that ref mute will implicitly cast to a star mute. Parent is none. Position is point origin. Rotation is quaternion identity. Scale is vector 3, 0. And then the same thing goes for oopsie. Same thing goes for the derived ones. And that's where we're going to start. And then now we need to do inner dot data equals self dot rows 0 self dot rows 0 last unwrap should be safe. I could actually do like a, let's do rust vec. I should have a last on there, but I don't. I want to just last returns an option. Do I need a mute? I do. I do need a last mute. Unwrap. I'm gonna leave that unwrap in there. I could do some kind of dumb unsafe thing, but as we learned from the incident with the renderer, with that render channel, doing unsafe things as a premature optimization is just gonna lead to buggy code. This is what we're gonna do. So last up, we're gonna just return this. So we're gonna do box into raw inner. And that is what we're going to return. So create node should work as intended. And now, oops. The only question left is how do we actually get at the scene graph? We somehow need to get a mutable reference to the scene graph. Ugh. And the way that we're going to do that is, I don't know. I don't know how we're going to do that. We know what the, whoopsie, I'm looking at the wrong scene, or the wrong file. So we know at the very least, Engine's going to hold on to the scene graph. We're potentially going to have multiple, multiple threads trying to create nodes at the same time. And so that's going to involve some degree of synchronization. What I would prefer to do, so the cheap and dirty way of doing this is mutex or RW lock, but I think mutex is kind of easier to wrap your head around because you don't have to differentiate between reading and writing. It's just, hey, give me mutable access to this thing. So I could wrap a mutex around the transform graph, and then this would be engine dot transform or engine dot scene graph dot lock dot unwrap. And then I could go from there, assuming I had a way to get at the engine. We actually know that this is like engine instance. That's super unsafe, but who cares? I certainly do not. The problem is that's really coarse-grained, and is going to potentially cause a number of other problems. For one, coarse-grained, locking the mutex on the entire transform graph means that I can only have one thread accessing the entire transform graph at a time, which kind of undermines exactly what I was talking about, where I'm specifically limiting the number of ways I can interact with the transform graph to make it safe to access from multiple threads at the same time. The idea being, if I only make local transformations, if I only make local translations, scales, and rotations to any node in the scene graph, it won't affect any of the other nodes, and it's safe to do in parallel. And since we know that what was I talking about? Where are my rows? Oh, I don't have a good way to visualize this, but since we know that the contents of each row is never going to reallocate, if we could atomically add a new element, like add and push and pop elements off of the transform graph, then we would know that it would be safe to construct new nodes in parallel. So actually, I'm scaring myself a little bit, but I'm thinking I'm going to get rid of Vec. This sounds crazy, but I think I'm going to rewrite a special Vec right now that is an atomic stable Vec. So the properties that I need from this Vec, I need it to be atomic. I need to be able to push and pop elements from multiple threads and not have any data races. So really all that means is that the counter internally has to be atomic. And I already talked about I want it to be stable. And in order to make it thread safe, it has to be stable. Pushing and popping elements can't reallocate the whole thing. Otherwise, it's going to potentially, that change is going to propagate to other threads. I mean, in theory, if I wanted to make it non-stable, but still support multi-threaded concurrent access, I could make pushing and popping in the cases where it doesn't need to reallocate happen atomically, and then the case where you do need to reallocate locks the entire thing, reallocates, and then unlocks it and allows other threads to continue mutating it. And that would be a nice middle ground. But since I already have the requirement that it doesn't move anything when it reallocates, when it tries to get more space for itself, I can apply that constraint to the entire thing, and you basically, I could write a vector type that only needs very little synchronization for concurrent access. And I can't really move forward without this. I mean, the only way to move forward without having this atomic stable vec is I'd have to wrap the whole thing in a mutex, or like wrap the first row in a mutex, but really I'd have to wrap each row in a mutex. And I don't like the sound of any of that. So I think now is a good time to call it quits for today. I've gotten off to a bit of a good start, even though I didn't actually write that much code. That seems like a running theme. I'm going to think about this over the weekend a little bit. I think I'm going to have some time to stream on Sunday. I'm going to think about what the requirements on atomic stable vec are going to be. In terms of just pushing and popping and not reallocating, that sounds a-okay to me. The one other requirement that I haven't talked about yet is swap remove. We want all of our data in our vec to be contiguous. So let's say I need to remove, let's say I destroy a transform that's in the middle of a row. If I can't just, it's a vec, it's contiguous, so I can't just remove one out of the middle. So to get around that, we do a swap remove. We take the one that's at the end of the row, move it into the spot of the one that was removed, and we already know how to rehook up pointers after when one of these transform data nodes moves in memory. That's already a requirement since we have to be moving them between rows anyway. So atomic stable vec, the other thing that has to be atomic is swapping two elements within the array, or not. I mean, I don't think I need general support for swapping, but at the very least I need the ability to atomically to swap remove. And so I'm gonna have to think about it. I'm gonna have to think of if if it's generally possible to swap remove elements within this vec, and if that's not the case, if it's not possible to do that safely, I'm gonna have to do some thought. I'm gonna have to see what it's gonna take to implement this transform graph in a multi-threaded way that reduces synchronization as much as possible. All right. Well, I'm glad I've made some progress. I hope this was interesting or insightful in some way. Thanks for joining me for the stream, and I will see you whenever I do this next.